Okay, so I'm very happy to have Parikshit Gopalan from Apple. I don't know why I don't have another affiliation, but okay, Apple. And you have up to 2 hours, as long as you need.
Okay, fantastic. Well, thank you. Firstly, I want to say it's such a pleasure to be back at this, place which always felt to me as the center of gravity of DCS. It's fantastic to see that this is going to continue for the foreseeable future. I'm going to talk about the communication complexity of distributed estimation. If you don't know what distributed estimation is, that's because it's a problem that we introduce in this work. So I'll tell you what it is. This is joint work with many fantastic collaborators, including Raghu, Prasad, Avi himself, and Mihir Singhal, who is a graduate student at UC Berkeley. All right. So communication complexity, the classic two-party model was introduced by Andy Yao. So the model there is that there is some function f that we're trying to compute. Usually this function f is a Boolean function, but we're going to allow it to take on real values as well. There's two inputs. Alice has a bit string x, which is n bits long. Bob has a bit string y. And now their goal is to compute this function fxy. And Yao asks, how many bits do they need to exchange in order to compute this function, right? And this gave rise to these two fundamental measures of complexity of a function, d of f and r of f, which are respectively the minimum number of bits that must be exchanged in the course of any deterministic protocol for f and randomized protocol for f. Now, this model has been, it's been a tremendous success. It touches almost every single sub-area of DCS, and Avi has a wonderful talk about this, which I saw this when I was a grad student. I'm not sure if it's on YouTube somewhere, but Avi?
Yeah, it's good thing to check. It's an old talk. I didn't get it for a second.
Anyway, so even with models which are, so successful and beloved as this one, sometimes a bit of change, some new problems is good, right? That's what we're going to do in this. Obviously there's been 2 whole books written on this topic, but sometimes new problems, a bit of change is good, right? So that's what we're going to do in this work. We're going to introduce this problem called distributed estimation, where as before, you have a function fxy on the inputs. The change now is that Alice will have a distribution p over 0, 1 to the n rather than a single input. Bob will hold another distribution q. And their goal is to estimate the expectation of fxy when x is drawn from p and y is drawn independently from q to within an additive epsilon. Okay? So now there are 2 parameters here. There's the input length n and there's this error parameter epsilon. We want to know how many bits must they exchange in any deterministic or randomized protocol, which gives us an epsilon approximation of f. Now, of course, there's also an error parameter delta for randomized protocols, but we'll suppress that because that's easy to amplify and so on. Now, you could ask, what is an interesting setting of epsilon? And the answer is everything, right? This expectation is going to lie in the range 0, 1. So you can start off by thinking of epsilon as a constant. You could think of epsilon as 1 over poly n. You could think of it even smaller. And certain things will change based on the setting of epsilon. But before we get into all that, why should we study this problem? Well, I think the first and foremost reason to me is that this is an extremely natural and clean extension of Yao's model, where instead of singleton inputs, each of the players holds a distribution on inputs.
Sorry, Parikshit, can you go back to the previous?
For sure. Yeah.
X and Y are
so now
n strings?
Yeah, let's say they're n-bit strings. Sometimes there'll be values. You can think of any domain for the inputs. There'll be also interesting problems so they come from the interval. But now Alice draws X independently according to her distribution P. Bob draws Y according to his distribution Q.
What do you know about F?
Oh, F is known, it's just like in communication complexity. Let's say they are trying to compute equality. So they know the function up front.
So for example, equality is a good thing to think about.
Equality is going to be our canonical example here. Yes, equality, set, disjointness, greater than, all the classics. You can think about any of them in this model.
Okay.
So, and we're going to talk about it in just one slide. So, just we'll see an example very shortly. Okay, firstly, I think this is extremely natural, which I think is the main reason to study it. But it also turns out that this is not exactly a new model. People have been implicitly looking at this problem, driven by applications in areas like sketching, databases, and learning, right? Now, in these applications, they will look at specific functions, like all the classics, equality, set, disjointness, something called absolute difference, which I'm going to define in a while. And also, they'll think about certain restrictions in the protocols which are driven by these applications. For example, it could be a one-way protocol, it could be a simultaneous protocol, there could be some other restrictions on this. What we're going to do in this work is say, look, underlying this, they're trying to solve a communication problem. We're just going to study this communication problem without these restrictions. Okay. Okay, so let me tell you what these examples are. So here comes equality. Of course, in communication complexity, the very first function you study is equality. Even in distributed estimation, equality has been studied for a long time in the sketching community, starting from the seminal work of Alain Matthijs-Szegedy, which introduced the streaming and sketching model. And it basically amounts to sketches which allow you to compute the inner products between two real valued vectors, which is basically a fundamental problem in sketching, right? So why is that? Well, let's just go through what distributed estimation means for equality. Alice has a distribution P, Bob has Q. They want to know the expectation of the equality function on XY, right? So this is one exactly when X and Y are the same. So it is just the collision probability of these two distributions. It's the inner product of P and Q. So what is known about this? The famous AMS sketch, Alain Matthijs-Szegedy, and count sketch, right? These are both sketching protocols. This is due to Charikar, Chen, and Farah Colton. They give you simultaneous protocols where the communication is 1 over epsilon squared. The error bound is something even stronger than what we wanted. We just wanted epsilon times, we just wanted epsilon, like epsilon times the 1 norm of P times the 1 norm of 2 of Q. They'll give you a bound in terms of the two.
Maybe you should say what simultaneous possible.
Oh, what is a simultaneous protocol? Okay, so what is a simultaneous protocol? It's where Alice and Bob just look at their inputs and they send a message to a referee. And the referee can look at these two messages and then decide what the value of the function is. It is the simplest model of communication. A one-way protocol is where Alice talks to Bob, sends one message to Bob, and then Bob is basically playing the role of the referee and announces the value of the function. And then you have multi-round communication where they talk.
Simultaneous is the weakest.
Simultaneous is the weakest, yes. Okay. Okay, good. Improving on this, we have this famous count-min sketch due to Kormor and Muthukrishnan, which is a simultaneous protocol. It only gives you only requires 1 over epsilon communication. It won't give you the stronger error bound. It will just give you an error bound of epsilon. Okay. Okay, so the question we want to know now is what happens if you allow unrestricted number of rounds of communication? Like, does it stop at 1 over epsilon? Can you get like log 1 over epsilon? Does it land up somewhere in the middle? Maybe 1 over square root epsilon? What's the right answer here? Okay, joint size estimation, right? So joint size estimation, it is a problem from databases. Some might say it is the problem from databases. So what's the problem here? Think of this graph, right? You have applicants. Each of them has a certain subset of skills that they possess. This is represented by this bipartite graph on the left. So this graph I'm storing in one database table. Then on the other hand, there are employers and they have jobs. And let's think of jobs corresponding to a certain set of skills. And the employer says, I'm willing to hire anyone who has any of these skills. Okay.
Many
So-
people in the audience will probably sure this is an HDX.
Yeah, don't you have triangles?
That's a clique complex.
Just the up-down walk, no?
So I'm sure there are fundamentally distributed estimation problems on HDXs that I hope you'll study on. Okay, great. So an applicant matches a job if there's some intersection between the set of skills the applicant brings and the set of skills the job is looking for. The joint size is the number of matches between these two. So these two have been stored as two distinct tables, right? So the joint size is the number of matches here. And, if you do up to some renormalization, we're just looking at distributed estimation for our favorite function in communication complexity, which is set disjointness. The way we have set up distributed estimation, you can always complement functions for free, right? Because f versus 1 minus f added to epsilon is the same thing. Great. What was known before was an upper bound of n over epsilon squared and a lower bound of n over square root epsilon, right? And to give away the punchline, we'll see improvements to both these bonds, but we won't get tight bonds for this. I mean, it's set disjointness. It's got to take a few years, right? Okay. And lastly, the thing that drew me into this, and my favorite example really, is something called expectation estimation for convex functions. So this was something motivated by this notion called omniprediction, which is a very strong form of learning. We were particularly interested in omniprediction for the setting where the labels are not binary, but they're real value. I won't tell you all about that, but there is a rather long talk from 2 years back that I gave here that you can watch if you're interested. So in order to do this, we needed to solve the following very concrete communication problem, which I'll call expectation estimation for convex functions. Alice has a distribution P on the interval 0, 1. Bob holds a Lipschitz convex function, again on the interval 0, 1. And the goal of the protocol is to estimate the expectation of f under Alice's distribution to within an additive epsilon. It's a very natural problem. And if you ignore the convexity, right, you can think of Alice just making epsilon with buckets and telling Bob how much probability she has in each of those buckets. This will give you a 1 over epsilon protocol. It uses Lipschitzness. It does not use convexity. The question is whether convexity buys you anything. And to me, a surprising result which we proved is that there is a deterministic one-way protocol for this problem, which has communication 1 over epsilon to the 2/3. Okay. And in fact, this protocol had a certain special structure. We'll talk about it more. But anyway, what does any of this have to do with distributed communication, as one of our reviewers for the conference asked? Well, it turns out this is an instance of distributed estimation. It is distributed estimation for the absolute difference function. The absolute difference function, it has two arguments, x and y, which both lie in the interval 0, 1. And the absolute difference is just the absolute difference of x and y. Right? So why is this expectation estimation the same as this distributed estimation for absolute difference? Well, we didn't realize this for a really long time, but the proof, when you see it, is just one line. Bob's function is convex. You can write it as a convex combination of functions, absolute value functions, or the form x minus y, where y is telling you where the minimum of the absolute value function lies, right? You can write it as a convex combination of these functions. And now this gives you Bob's distribution, right? Because already there was a distribution on x, and now this decomposition of the function is telling you the distribution on y. So now they're just trying to solve distribution estimation, absolute difference. So yeah, they're trying now they are trying to answer the question, what is the expectation for x drawn from P and y drawn from Q of the absolute difference of x minus 1? So this is another instance of distributed estimation.
Can you explain again how you?
Yeah, good. So here's what I want you to do. Expectation under x drawn from P, Px. But now this function is itself a convex combination of absolute value of x minus y functions, right? So think of y as the minimum point. If y is half, it's this nice symmetric function. If y is 1/4, then you're just moving this thing around, right? So now plug this in here. We have expectation under x sampled from P. This is basically an expectation of x minus y under this distribution on Qs. So therefore, it's a double expectation under these two distributions.
But it's clear that IF can be written this way?
Oh, yeah. I mean, this takes a little bit of work. It's not very hard. It basically is because what's the derivative of the absolute value function, right? It's a step function. It jumps from -1 to 1. And what are convex functions? They are basically functions where the derivative is monotone increasing. So this is basically stemming from the fact that every monotone increasing function is a convex combination of step functions, which we use all the time.
Yeah, here n is not explicit, but it's just some representation of this real value.
That's right. And here you can always assume this n is log 1 over epsilon. So here really there's only one interesting parameter, which is epsilon. And we'll see that when we talk about this. You guys are trying to solve this problem already as sense, which is how I remember seminars in this place going. We'll come back to each of these three problems in turn. Okay, so I'm still on motivation, really. There are other examples which seem very natural to me. I'm not aware that people have studied communication in these scenarios or that, it's particularly urgent, but it seems natural enough. If A were the payoff matrix for a game, then P transpose AQ is just the value that you get when Alice plays strategy P and Bob plays Q. If it's the adjacency matrix of a graph, then this is you can think of subsets and the number of edges induced in a particular rectangular subset and so on. All right. Yeah.
Maybe I should let it pass, but this is an example of distribution estimation?
Yeah, sorry, yeah. But what would be the function here? The adjacency matrix, which is 0, 1, it defines the function, which says that think of the vertices as bit strings, okay? That's x and y. This is telling you that f is 1, for which x, y pairs is x1, where you have an edge. That's the function.
Okay, usually it's saying that the pair of questions is not uniform.
Oh, okay. So this is just edge density for rectangular subsets, like in Zemerides lemma, right? So this distributed estimation will say, if you have a subset, a bipartite graph, you have a subset A on the left-hand side and a subset B on the right-hand side, what is the edge density between those? So it's a restricted. Yes, thanks. Okay, great. Okay, I hope I've convinced you that this is a problem that shows up naturally in a number of different settings. Now, maybe the next thing to ask is that, well, we have this thing called distributional complexity in communication complexity. How is this different from that? Is this just a repackaging of the notion of distributional complexity? So, does anyone think this question is worth asking? Otherwise, I can just skip over it, right? So distributional complexity, just to be very quick, it's back in Yao's two-party model. You're fundamentally thinking of protocols which take X and Y as inputs, and they give you an answer, right? And then we're trying to come up with a hard distribution on inputs where any protocol will require a lot of communication. When you move to distributed estimation, the type of your protocols changes. They take distributions as inputs and they output a value. And now we're not looking for some one bad distribution. We're looking for protocols that work for any pairs of distributions. Right? So there's just some superficial similarity, but it appears that none of you are confused by this. So, I shouldn't have brought this up. Let's move on. Okay. How does distributed estimation relate to the standard model? So I'm going to remember this notation I introduced, R bar epsilon F. It's the number of bits that Alice and Bob must exchange in order to compute an epsilon additive approximation to the expectation of. So I claim that this quantity lies sandwiched between R of F. What was R of F? It's just the randomized communication complexity of F in the standard two-party model. So I claim that it lies sandwiched between R of F and R of F over epsilon squared. The lower bound, it's quite simple. Just imagine that Alice and Bob have point distributions, right? So they really just have X and Y. And now I'm telling you to find the expectation over this single distribution. That's just telling you asking you what is F of X, Y, right? So of course they have to be able to solve just singleton instances. That's where the lower bound comes from. The upper bound comes from a simple random sampling protocol that's going to show up time and again in this talk. Alice samples k points from her distribution P. Bob samples k points from his distribution Q. They just compute the average of f, xi, yi over all these pairs, and they say that's my estimate. Right? And now a simple variance calculation / chain of bound will tell you that once you have 1 over epsilon squared samples, then you're going to be within epsilon of the true expectation. Because each of these samples, fxi, yi, is an unbiased estimator of the expectation, and these k samples are independent.
I'm kind of assuming that computing one instance is, and if you allow this epsilon additive error, it might be even easier.
Good. Yeah. So what Irith is asking is, did we really need to do this, right? So you could do it by solving 1 over epsilon squared independent instances of f. What do we need to? If you had to guess, what would you guess? Okay.
Is there like a probability of failure necessary for the definition of your model?
In randomized, I think so. I mean, necessary in the sense it makes for a richer model, right? If you don't allow me probability of failure, I might get terrible samples and then this upper bound won't hold. So I'm allowing.
Sure, sorry, I just mean ignoring the connection to randomized communication complexity, just the definition that you started with. Does this include some small probability?
You could have a deterministic protocol which never fails. And you'll see some non-trivial, there are some non-trivial deterministic protocols which will never fail. But randomized, you always do sampling and you always live in fear of bad samples. So that can, for randomized.
But the answer is yes. You said it in the beginning that we ignore the small probability of error because we can amplify.
Yeah, we'll ignore it, but it exists. Yeah.
So if your protocol is one way or simultaneous, then you can compute fxi and yj like for all pairs ij. So this is diagonal term, and you can actually get the rectangle.
Yeah, but are those independent?
What do you?
Would those be independent samples?
Oh yes, yeah. The independence is yeah.
I love this. Yeah, we'll come to your comment on slide number 45. More questions? Okay, great comment. Okay, so then these are the questions that we'd like to answer when we're trying to build a theory of distributed estimation. First and foremost, are there non-trivial protocols? And by the end of this talk, I hope to have convinced you that the answer is a resounding yes. There are very non-trivial protocols here. Sorry. What is hard versus easy in terms of epsilon? When we talk about randomized communication, we know that having linear in end communication for Boolean functions, those are our hard functions, set disjoiners, inner product. Having communication log n or constant in the public coin model, that's equality greater than. So you see the full scale. What does hard or easy mean in terms of epsilon? At this point, we have no idea. Then once you've decided what is hard and easy, you can ask what makes functions easy or hard? Is it some property of functions you are familiar with from Yau's model, or is this something new? And finally, since epsilon is the new parameter here, how do you even show lower bounds as a function of epsilon? So these are the questions that we're going to address in this talk. Okay, let's start with upper bounds. And we're going to, okay, before we start with the problem, we're going to use this extremely standard fact from probability and statistics. It's variance reduction using sampling. So the setup is this. X is a random variable whose absolute value is bounded by beta. So it never takes values larger than beta. Beta is a value in 0, 1. Now suppose I draw k independent samples, x1 through xk. And then I estimate the expectation of x by the average. So this is what I'm trying to do. I'm trying to estimate the expectation of x. So I do it by drawing k independent samples and averaging them, right? Then, of course, this is an unbiased estimator for x. And the variance drops can be bounded by beta squared over k. Beta squared comes because absolute of x is bounded by beta. So, of course, its second moment is bounded by beta squared. And then you get this k additional gain, right? So what this tells us is that if I want an epsilon additive approximation to the mean, I want my variance to be like epsilon squared. So taking k is equal to beta squared over epsilon squared samples suffices to get additive error epsilon. So of course, if all you know about x is that it's bounded by 1, then tough luck. You'll get 1 over epsilon squared, which we just got in the previous slide. But if you're able to make this beta small as a function of epsilon, for example, if you're able to make beta root epsilon, then you'll start to see better bounds here, like 1 over epsilon. You know, the sky is the limit. If you make beta really small, you'll get really small sample complexity here. Yeah.
Do Alice and Bob know their distributions, or are they only
Yeah,
the sample?
The distribution, oh, great question, great question. Either works. For proving lower bounds, we'll assume that they know everything about the distribution. But if you look at our protocols real closely, you'll see that they communicate very simple statistics like the mean, expectation, and so on. So samples would suffice. And more generally, you can say that, you know, the first thing I'm going to do is to replace Alice's distribution by 1 over epsilon squared samples and Bob's distribution by 1 over epsilon squared samples. So now, you know, that's all they need. And this is going to be, if they can do it for this empirical distribution, that's good enough. So in some sense, great question. I wanted to have a slide on it, but I didn't. Okay, let's go back to distributed estimation for equality. There was a few slides ago, so let me remind you that given P and Q, we're trying to compute the collision probability. What we've seen is a 1 over epsilon protocol for P and Q for computing this inner product. I'm going to tell you, oh no, we haven't seen the protocol. We've seen that there exists a protocol. Now we'll actually see the protocol. Okay, it's extremely simple. Let P delta be the vector of delta heavy elements of P, which basically means you look at P. If this coordinate is larger than delta, you let it be. If it's smaller than delta, you zero it out. Right? So this is often called the head of the distribution. Since it contains the heavy elements, it's 1 over delta sparse. And P less than delta is the tail. It's all the small stuff. Okay. Now in the one round protocol, we'll set delta is equal to epsilon. Alice will just send P epsilon to Bob. Right? That's just 1 over epsilon elements. Bob will compute the inner product. And who cares about the tail? It's small stuff anyway, right? They just ignore the tail. The claim is that this is already good enough to give you an epsilon approximation. I'm sure everybody sees it, but I'll still belabor the proof, right? Why is this correct? I wanted to compute P dot Q. I actually computed P epsilon dot Q, right? So what did I miss? I missed exactly the inner product of the tail, the P less than epsilon times Q. But what is P less than epsilon times Q? It is the expectation of the vector P less than epsilon under Bob's distribution Q. And since this is bounded in L infinity by epsilon, by definition of the tail, this can be at most epsilon, right? So therefore, we only miss epsilon, right? How many bits did they need to communicate? Well, the naive thing to say is that Alice just sends Bob the names of all her heavy elements. That would cost you n over epsilon bits. I'd be happy with that, but if you're a stickler, the first thing you can do is take this universe of size 2 to the n and hash it down to something like poly 1 over epsilon elements, 1 over epsilon squared. Then convince yourself that this inner product hasn't changed much, right? But what has happened now is that the names of elements are only log 1 over epsilon bits. So when you do this, you'll get a protocol with communication O tilde 1 over epsilon. And you should pat yourself on the back because in essence, you just rediscovered count min sketch due to core moding with the Krishna. This is exactly what it does.
So the hash then should be known by both, it's being sent to the referee. So the referee knows.
We use public randomness.
Okay.
Thank you. So in all my randomized protocols, I will assume public randomness. Right? So they just hash down, they say it's 1 over epsilon squared universe, and then everything proceeds. So in one round, you can do 1 over epsilon. What happens when you have multiple rounds? Okay, so here's a 2-round protocol. We're going to start with the same decomposition into head and tail, but we don't want to send the entire head, right? We don't want to send 1 over epsilon bits. So what we're going to do is to set this delta parameter to be much larger than epsilon, and we'll see in a minute what the right setting is. So we're going to do this decomposition. In the first round, Alice will send the head to Bob, and he'll compute the head part. Right? But now we've set delta larger than epsilon, so our error is pretty large, and that error is coming from the tail. So now you can't just ignore the tail, you've got to do something about it. So here's what they'll do. We'll use this observation that the tail is the expectation over Bob's distribution. So Bob is going to sample k times from his distribution Q. He'll send this to Alice. Alice is now going to estimate the tail using the average of these samples. What did Alice gain here? She gained that she's trying to estimate just the tail part, not the entire thing, which is what random sampling does. And now we know that these variables are bounded by delta. Right? So it's perfectly set up to use our variance estimation lemma. The variance is now bounded by delta squared over k. And we want to make this to be epsilon squared. So, there's some nice symmetric setting where you said delta is 1 over k is epsilon to the 2/3. That will balance out the 1 over delta you need in the first round with the k that you need in the second round. What ends up is that you have a protocol whose communication is O tilde 1 over epsilon to the 2/3, right? So we're doing great. 1 round was 1 over epsilon, 2 rounds is 1 over epsilon to the 2/3. Where is this headed? Okay, we'll see. Let's keep some suspense about this. But what I want to abstract out of this is the following template, which seems very powerful and useful. Just using random sampling in 1 round, you could have done 1 over epsilon squared. Didn't seem particularly impressive. We instead found a deterministic protocol, which in 1 round gave us 1 over epsilon, forget the end, let's hash, right? And then by combining this deterministic protocol with random sampling, in 2 rounds, we managed to go down to 1 over epsilon to the 2/3. Okay. And of course, the main question now is this the right bound or can we go further? I will not answer that and I'll instead move to a different problem, which is absolute difference, which is my absolute favorite problem in this whole thing. So the absolute difference problem, you have x and y, which are values in 0, 1, and the absolute difference is absolute value of x minus y, right? And let me just tell you where this problem came from. It was expectation estimation. Alice had a distribution on P, Bob had a convex function f. Their goal was to estimate the expectation to within epsilon. Right? So what this result in this paper with Princeville, Prasad, Abhishek, and Mihir did is not only did it give a deterministic 1 over epsilon to the 2/3 protocol, it actually gave an approximate basis of 1 over epsilon to the 2/3 functions. Alice picks these functions in advance. She tells Bob the expectation of these functions, and then she goes away. And these functions are the property that once you know their expectations, you know the expectation of any Lipschitz convex function, right? So it had this stronger property. And what they proved already is if this is what you need, if you only allow expectations of functions, you cannot do better than 1 over epsilon to the 2/3. But here we are like, oh, that's too restrictive. We just got to think of it as a communication problem. And now what is the best you can do? let's say what's the best you can do in one round. Even that's not clear, right? Okay. So we're going to see a deterministic one-way protocol, which only uses 1 over square root epsilon communication. And the key definition which makes this possible, so this whole thing is made possible by the following nice definition. It's that of a regular partition of the interval 0, 1. So let P be some distribution of the interval 0, 1, and let beta be some regularity parameter. I'm going to say that a partition of the interval 0, 1 is beta regular for P. It's a partition into K intervals, and every interval satisfies the width of the interval times the probability of that interval under P is at most beta squared. Right? So at first cut, just think of asking that the width of the interval is bounded by beta and the probability of the interval is bounded by beta. If you can do this, you're great, right? But we may not always be able to do this. Why? Well, there could be point masses. Yeah, exactly. There could be point masses, right? But even if I have a point mass, I can make the width really small. So I can always achieve width times probability is at most beta squared. And in general, it's very easy for Alice to construct such a partition greedily, and it will require K is equal to 1 over beta. So this is going to be our main tool in coming up with a better protocol. Okay. So here's the protocol. Alice will compute a beta regular partition for P, and then she's going to send Bob for every interval. She'll tell him the following things. Firstly, what the interval is, meaning what's the endpoint, right? What is the probability of this interval? Now, of course, these intervals are fairly small width, but she'll tell him the probability of this interval and the expectation of X conditioned on that interval, right? So so these are the three things she's telling you. What is the interval? How much probability does it have? And what is the expectation of my input condition? Already, if it's a small interval, Bob knows that the expectation lies somewhere there. But she nails it down for him and tells him exactly what the expectation is. Okay, now I'm going to set up this slight simplification of notation. I'm going to write P is equal to Pij, Pj is equal to Pij, Qj is equal to Qij. Why am I doing that? So I can fit this all on one line. Okay. So the expectation of the absolute difference of X minus Y, I'll just split it up based on which intervals Alice's input and Bob's input fall into. And I'll distinguish between two cases: collisions in the intervals and no collisions in the intervals. The head corresponds to the setting where X and Y, they fall into different intervals. The tail corresponds to the setting where X and Y fall in the same interval, right? And it turns out that it's a very good idea to separate out the head from the tail. Why is that? Well, condition of the event that X and Y fall in different intervals, you know which of X and Y is bigger. So absolute value of X minus Y, you can get rid of the absolute value. It's just a linear function. In particular, if J is greater than K and X lands in Ij, that means X is greater than Y. So absolute value of X minus Y conditioned on this event is the same as the expectation of X conditioned on this interval, landing in this interval, minus the expectation of Y conditioned on landing in the interval. Now, this thing Alice has told Bob. This thing Bob knows because he holds the distribution. So this means that every single term in this first summation, Bob can compute it based on Alice's message, right? That's the head. What are we going to do with the tail? Well, at first, we ignore it. And why we can ignore it is by regularity. So if you look at the tail, I'm going to rewrite it. I'm going to do this very clever trick of interchanging the order of Q and P because multiplication is commutative. So I can write it as Qj times Pj times expectation X minus Y conditioned on them both lying in the jth interval. But this difference, if they both lie in the same interval, is at most the width of Ij. right? So this is bounded by Qj times Pj times width of ij. That is exactly the quantity that regularity bounds by beta squared. So once again, it's the expectation of a beta squared bounded variable. It's at most beta squared, right? So at this point, we've said that the head requires communication 1 over beta because there's 1 over beta intervals. The tail is bounded by beta squared. So if I want an epsilon approximation, I'll send beta is equal to square root epsilon, and I got a 1 over square root epsilon protocol in just one round. Okay. Okay, so no marks for guessing what's going to come next. We're going to reduce the error of this protocol by random sampling, right? And if you've seen equality, you know how this is going to work out. So don't worry if the technical details don't make sense. We have the tail, which is the expectation of a random variable. There's only two things that you need to know about this random variable. One is that it's bounded by beta squared. And the other is, if Alice tells Bob what y is, then Bob can sample this random variable because, the other way around. If Bob tells Alice what y is, Alice can sample this random variable because she needs Pij, that's just looking in which interval is y and computing the probability of their distribution for that interval. Then Alice needs to compute this other somewhat more complicated thing, but she can do it, like the sign changes, but Alice has this distribution now, so who cares? Okay. So now again, Bob will sample k times and send these samples to Alice. She will in turn sample this tail variable ty1 through tyk. She'll estimate their mean. And now because we have a beta squared bound, that translates into a bound of beta raised to 4 over k in terms of the variance. We want to make this at most epsilon squared. So again, there's a nice symmetric setting of parameters, which ends up spitting up this rather strange number. You take beta is equal to 1 over k is epsilon to the 2/5. This gives you a 2-round randomized protocol whose communication is 1 over epsilon to the 2/5. Right? It's a fairly strange number. Is this tight? Again, okay, so I'm not going to answer that question, but again, the template was exactly the same as we used in equality. You have random sampling, you have a good deterministic protocol, you combine them and you get something non-trivial in 2 rounds. Right? And this is the whole point of not doing one problem at a time. When you put them all together, you start to see the forest there, right? So this general recipe that I've shown you of deterministic approximation followed by variance reduction gives you a bunch of upper bounds for a lot of different functions. For greater than, you get n over epsilon to the 2/3 in 2 rounds. Curiously, greater than is thanks to Avi, we know that it's the signature function where you can reduce the communication by using more and more rounds, right? So if you use more rounds, you can get this n down to log n. But the epsilon to the 2/3, it stays there, and for a good reason, as you'll see. If you have a function of 2 variables, which is Lipschitz in both these variables, then you can get 1 over square root epsilon in 2 rounds. Lipschitz is like bounded first derivative. If you make stronger smoothness assumptions about the function, which you can imagine makes it easier to approximate somehow, then the communication drops to 1 over epsilon. The exponent of epsilon becomes 1 over k plus 1. So it can really go to 0 as k becomes larger and larger. Okay.
So what were we using about hashing before that then doesn't work here for the
For greater than?
Yeah.
It's the fact that the identity of when you hash, you will not be able to do greater than.
Oh yeah, right.
Identity matters in greater than, but not in identity and equality. Yeah. Okay, so now we have all these weird exponents, and surely you're wondering, where do these come from? Is there any reason to believe these are the best possible? But I claim the really burning question is the question which was asked by Irith and someone else at the start, which is, can you beat Rf over epsilon squared for general F? And we have this template. Let's use it. Let's try and come up with. So when I say general f, I just want to assume that f is bounded in the range -1, 1. No other assumptions about f, right? Now we have this general template where we first come up with a deterministic approximation and then we do some variance reduction. We could try that, except we have no idea how to get started. Getting a deterministic approximation for general f, I don't know, maybe it can be done, but I don't know how to do it. Right? So let's go back to this level. There's two parameters here. There's beta squared and there's k. If we can't improve on the beta squared, maybe we should improve on k, as you suggested earlier. So how do we do that? Well, let's go back to random sampling. So we have these case samples for Alice and case samples for Bob. In our unbiased estimator, we wanted independence. So we only took these pairs, x1, y1, x2, y2, x3, y3. But let's just imagine that Alice and Bob were sending each other in this protocol. Let's just imagine Alice sends her x's to Bob, right? Bob has enough information then to compute many more estimates, right? They can do xi, yj. Each of these is an unbiased estimate. The whole point is that they're not independent, right? But what happens if you take this estimator, 1 over k squared times summation xi, yj? Does the variance drop as 1 over k squared? For instance, in PCPs, we have examples where things which shouldn't be independent in any way, they behave like they're independent, if the right people do the analysis. So maybe something like that will work in here. Okay. However, this fails, and it fails badly on the simplest example. The simplest example is that you just have a rank 1 matrix where some rows are all ones, some rows are all zeros, right? And now it doesn't matter how many columns you take, right? You need to sample more rows to get the variance down, right? Like if I take x1, y1, x1, y1, x1, y2, x1, y3, these are completely dependent. There is no new information there. So this is just like I'm sampling a 0, 1 random variable k times, and my variance is going to behave as 1 over k. There is no 1 over k squared to be had here, right? So this fails, and it fails rather badly.
That's because the function is
boring.
It's
rank 1.
It's tailored to the rectangular nature of your set.
Right. Yeah. I should have a more convincing.
It's not about not convincing. It's this can work for some functions and fail for others.
That's right.
Can you add a random mask on it? Like you take some function g with small communication complexity, and then you write f as f minus g and g, f minus c plus g. So ideally, f minus g should be pseudo-random enough that avoids this rank 1 obstacle, and g itself is something simple as well.
I'd have to think about it. It sounds like you could. But the point is, even this naive idea can be made to work. You just need the right estimator. And this is something that we call the debiasing estimator. What is it? My new estimator, given x and y, is the slightly more complicated thing. I first draw the first coordinate a at random. I look at the expectation fay for random a and fixed y. I do the same for randomization over the columns b. And of course, the scale is not right, because if the function is basically the same value everywhere, I'm going to get twice the expectation. So then I subtract out fxy. Okay. So this is what I call my debiasing estimator. In terms of a picture, imagine that this point here is x, y. So I first take the row average, then I take the column average, and then I subtract out the value xy sitting at the center, which kind of got double counted. Okay. What is nice about this estimator? Well, it's an unbiased estimator. But here's the cool thing. It is an unbiased estimator of E of f just for random choice of x in P. It is also unbiased if you just choose y in Q at random, but you don't need them both to be random. Either randomizing over rows or randomizing over columns is sufficient to give you an unbiased estimate. Okay, this proof, it ought to be a proof by picture. So let's see what happens when we randomize over the rows X, right? So, well, the first term here already didn't care about the row. It was randomizing over, the row in any case. So that stays the same. The second term, what is it? We are taking the average over the columns, right, for this specific X. And now I'm re-randomizing X over all the rows. So this will become the average of the whole matrix. And now what about the third term? The third term is just f of xy. And now when I randomize X over all the rows, it's going to be exactly the same as the first term, and they will cancel out. Right? So what you get is the overall expectation of the matrix. And of course, you can do the same thing by randomizing over columns instead of the rows. Okay, so you can write this down, but I think that's really the right way to think about the proof. Over a random X and P, the first and third terms become exactly the same, and the second term becomes the expectation of the whole function. Okay, great. The other thing about GXY is that computing it is reasonably cheap in terms of communication. So why is that? Well, the obvious thing Alice and Bob can do is to send each other X and Y. N bits, we're done, right? You can be slightly cleverer. If you have a one-way communication protocol where you can send something smaller to Alice, which still lets her compute fxy, we can do that. So this is what I mean by our one way of f. Think of this as Alice sends a sketch of X, which doesn't tell Bob what X is, but it'll tell him what f of xy is for any particular y. And by some standard amplification, it lets him compute this expectation over his distribution. So why am I emphasizing this so much? It's because if you have a multiple round protocol for computing X and Y, which is very cheap, like we have in greater than, I'm not sure how to use this for computing these expectations, because you can think of Bob having these k samples and they want to compute fxy for each of these samples. But then each of the k instantiations of the protocol, they go in different directions and I end up communicating k times what I wanted to. Whereas here, it's just one communication for every x and you're done. That's important. Okay. So don't worry if this doesn't make too much sense right now. We will revisit it later. But now let's finish the job we started. Let's prove one nice lemma about the debiasing estimator, which says it behaves the way we wanted it to, that the variance is going down really rapidly. So to analyze that, I'm just going to center this estimator. I'm going to subtract out the mean because mean zero variables are easier to analyze. So here's our key lemma. Let x1 through xk be drawn from P, y1 through yk be drawn from Q. Then the expectation of g hat applied to xi yj times g hat applied to xi prime yj prime is 0 unless ij is equal to I prime j prime, right? So this is basically saying that, look, if ij is equal to I prime j prime, this is just g squared, right? So it should not be 0. But any other time, it's 0, including in the crucial case when it's the same row coordinate xi and only different coordinates j and j prime. Okay. And really, this is all just, detail. The picture is the thing that you should take away from here. But why does this work? Well, we have xi, g hat, xi, yj, g hat, xi, yj prime. The dependence comes from xi. So let's condition on xi, right? So now if you condition on xi, you fix the row. Now what am I doing? I'm just sampling the same random variable twice and independently because I'm drawing j and j prime and these are independent. So their expectation of their product is the product of their expectations, and each of those expectations is 0 just because it's unbiased just over the choice of y's, right? So xi and yj, xi yj and xi yj prime behave like independent samples. And the upshot of this is the following. When you compute the variance, right, the variance of g xi yj, it's just the sum of these terms squared. So this is just some routine calculation. Only the diagonal terms survive. There's k squared of them. All the k to the 4 off diagonals, they go to 0. So the variance of the sum is bounded by k squared. And then I take the variance of the average then. I'm dividing by 1 over k squared, so I'll get a 1 over k to the 4th in terms of the variance. The variance of average actually behaves as 1 over k squared, like we wanted it to. Okay. So this gives us a debiasing protocol for arbitrary bounded functions where they sample x1 through xk and y1 through yk. They send sketches to each other. They compute these row and column-wise expectations, which we argued a sketch is good enough for that. This lets them compute the debiasing estimator for all pairs ij. They return the average. Right? So it's exactly what you would expect. Some things which changed is that random sampling could be done in one round. Alice samples first input, sends them to Bob and says, now you deal with it. Here they need to tell each other something because this expectation can only be computed by Alice and this expectation can only be computed by Bob. So you needed 2 rounds. But the nice thing is that the communication is scaling linearly with k, but the variance is dropping quadratically with k. We want the variance to be epsilon squared. So we set k is equal to 1 over epsilon squared. And we get a protocol that works for all bounded functions in 2 rounds and uses O tilde r one way of f divided by epsilon bits of communication. Okay. Any questions about the debiasing protocol? Okay, so where does this come from? There's 2 answers. One is Prasad. The other answer is there's something called the Efronstein decomposition of any function. This debias the debiasing estimator. It basically is related to the top term in the Efronstein decomposition. Okay. All right. So we are at the halfway point now. Let me just summarize what we've seen so far. I hope I've convinced you that there is a zoo of interesting upper bounds to be had here. We've seen 2 upper bounds, r one-way f over epsilon and rf over epsilon squared. These work for all bounded functions. Excuse me. We've seen 1 over epsilon to the 2/3 for equality. It also works for greater than. Then these other bounds, we saw this 1 over epsilon to 2/5 for absolute value. So what's the big picture here? We seem to be getting these weird exponents on epsilon. Is there some big pattern? Where are these numbers coming from? Okay. Also, more interestingly, there's this thin blue line, which you might not have noticed. There's no Boolean functions below this line. They're all real valued functions. Why is that? Well, we'll take a 5-minute break and then we'll talk about lower bounds. All right, so let's welcome to part 2. I'm surprised you're all back here. Let's talk about lower bounds. I just want to make one point here, which might have been lost in all the coughing. Like we have all these upper bounds, right, for various kinds of functions. We looked very hard. We did not find any Boolean functions which are easier than 1 over epsilon to the 2/3, right? Whereas for bounded functions, we've said that you can get arbitrary small exponents in epsilon. Right? Okay, so let's start with our most general upper bound. We have these 2 upper bounds, r one-way of f divided by epsilon and r of f divided by epsilon squared for all bounded functions. Let's take a really hard function for Yao's model. That means the randomized communication r of f and hence r one-way of f, which is only larger, is n bits, right? We know many functions like this, inner product, set disjointness, and so on. Both these protocols, well, this protocol is clearly beaten by debiasing, which gives an n over epsilon upper bound. Can you improve on debiasing? Can you get better than n over epsilon? N over epsilon, to the 2/3, for instance, would be really nice if you could get that. But it turns out that for the inner product function, our favorite function from communication complexity, which is the GF2 inner product of two strings, we show that you actually need n over epsilon. Right? So you cannot improve on debiasing for general functions. In particular, you cannot improve on it for inner product. The one thing we know about inner product is that it corresponds to the Hadamard matrix. We've known that the Hadamard matrix has high discrepancy. This is Lindsay's lemma. This theorem, you can prove a version of it, which applies to any high discrepancy function, right? So high discrepancy makes functions hard for distributed estimation, just like it does for randomized communication. Okay, if you only allow one round, then debiasing needs two rounds, because as we said, there's something that Alice needs to do, something Bob needs to do. Random sampling didn't need that. And if you only allow one round, then random sampling is optimal. Right? You need n over epsilon squared. Now, we do a lot of heavy lifting in this proof, but we also borrow a lot from the query to communication lifting literature, which Prasad, Raghu, and their co-authors have been working on for many years now. So this is a technically very involved proof. Okay. Now, let's talk about debiasing versus random sampling. They give these two bounds where in general, it seems like debiasing is basically doing much better. It has 1 over epsilon versus 1 over epsilon squared. But if you look at the numerators, then you realize, well, these are not quite comparable. Because here we needed a one-way protocol for F. Here we could do with an arbitrary multi-round protocol for F, right? Of course, your round complexity will increase, but your total communication stays small. And we know there are functions where there's a huge gap between the one-way and the multi-round complexity. In particular, there's this thing called the indexing function, which some of you might be familiar with. We'll see it in the next slide, where the one-way communication is linear in n, but the multi-round, even two-round, is logarithmic in n. So then if you look at these two bounds, this is giving you n over epsilon, this is giving you log n over epsilon squared. Which is kind of annoying. It would be nice if you could just get the best of both worlds, the better numerator and the better denominator, right? Which would be RF over epsilon. But it turns out this is not going to happen. There exists a function g where the one-way communication is linear, the multi-round is log n. So the two upper bounds we'd have is log n over epsilon squared and n over epsilon. And you can show a lower bound for 1 over epsilon squared for epsilon larger than 1 over n. 1 over n is the point at which these two bounds would be the same. And this is saying that below that, this actually random sampling wins. This proof is really nice. It fits on a slide, so I'm going to show you. Okay. I realize there is a certain it's kind of out of order. I'm not going to define the problem I'm reducing from, but it's going to be okay. So we'll just see the proof, right? Okay. So the function, we need functions for this separation. We need functions which they should have small one-way complexity. So sorry, just let me make sure what I want to say. Okay, so this function we are going to construct is called two-sided indexing, right? So just like in indexing, you have a string x, which is a Boolean string, and you have an index I between 1 and n. You have y and an index j. And the function is xj XOR yi.
You didn't define normal indexing.
Sorry? Oh, I didn't define normal indexing. Yeah, so therefore, in normal indexing, Alice would have x, Bob would have I, and they want to know the bit xi. It's hard only in one direction, because if Alice speaks first, she sends the whole string. If Bob speaks first, he sends the index, and they're very happy, right? This is just made so that, you need to use two rounds, no matter who speaks first, because Alice has a pointer into Bob's string. Bob has a pointer into Alice's string, right? So if you give them two rounds, they'll just tell each other the indexes, and then they will announce these two bits, and they'll XOR them very happily. If you restrict the number of rounds, somebody is going to have to scuff up the whole string. So it requires a lot of communication. The kids know indexing here. Okay, so I'm going to reduce from this problem called gap hamming. Gap hamming is just inner product over the reals, okay? And I apologize for this continuity gap. Gap hamming is going to show up a little later, but I'll just show you right now how gap hamming shows up naturally when you consider distributed estimation for two-sided indexing. Let's say that Alice and Bob have as inputs A and B, which are strings. They're matrices, but they're basically strings in -1 raised to n squared. What they really want to compute is the entry-wise inner product of these two matrices, right? It's just a glorious inner product over n squared length strings. Well, they have a good protocol for two-sided indexing, and this is how they're going to use it. Alice's input will be the ith row of the matrix A and the index I, for I chosen randomly from 1 through n. Bob will get the jth column and the index j. This is the set of inputs. This is the instance of distributed estimation. And what happens here? Well, it's kind of really clever. You look at G, Xi, Yj. So Alice now has the ith row of the matrix, and Bob wants the jth index of that. So that is exactly the entry Aij. On the other hand, Bob holds the jth column. Alice wants the ith bit of that column. That is Bij, right? And there's an n squared here because to account for the choice of ing. So what they're trying to compute is basically the inner product of these two matrices as strings. And there is a lower bound of this flavor for computing this inner product, right? So if they want this to be within an additive epsilon, they better be willing to pay 1 over epsilon squared as long as epsilon is greater than 1 over. Okay. So what did we learn from this? That these two, we're going to have to live with two incomparable upper bounds, because really there are some times when this protocol is better, there are some times when that protocol is better. Okay, great. All right, so now we'll come to what I think is the main technical contribution of this work. Well, one of the main technical contributions of this work. It's a spectral technique for getting lower bounds in terms of error, right? So this spectral technique will let us prove that all of the bounds you're seeing on this slide are in fact tight. Not just that, it will also prove that this blue line actually exists, and you cannot have Boolean functions which have communication complexity less than 1 over epsilon to the 2/3. No non-degenerate Boolean functions which have communication complexity less than 1 over epsilon to the 2/3. Okay. And I should point out that I'm saying that we have tight bounds for nearly everything. The one thing we don't have tight bounds for, of course, is set disjointness. Let me just tell you the state of the art for set disjointness in case one of you wants to solve it. Debiasing will give us an n over epsilon upper bound. That's the best upper bound we know. In terms of lower bounds, just because it's Boolean, you have a 1 over epsilon to the 2/3 lower bound. There's also this lower bound of n over square root epsilon, which is about 10 years old. And what is the right bound for set disjointness? We really don't know. It's entirely possible that there could be an n over epsilon to the 2/3 upper bound. It's also quite plausible that n over epsilon is a lower bound. Okay. So now let's talk about the spectral lower bound. So finally, gap hamming arrives a couple of slides too late. So what is gap hamming? Alice and Bob, they both have strings x, y in ±1 raised to k. And they want to know whether this inner product, x dot y, is greater than root k or it's less than minus root k. Right?
It's a promise problem.
It's a promise problem. And even with this promise, right, somewhat surprisingly, it requires omega k bits of communication. So this problem, this was first shown to be hard by Chakrabarty and Regev. Then Sasha Shurstov came up with a simplification. There's a recent, even more recent proof by Rao and Yehudayev. And Anup gives a talk in the seminar, so if you're interested, you can watch the video of that. Okay, so let me just say a few words about it. So here, this root k, she seems to show up a little abruptly, right? What happens if we say distinguish between xy greater than t or xy less than minus t, and t is less than root k? Well, that problem is only harder. If I say xy greater than 1 or less than minus 1, then of course the omega k lower bound will hold. On the other hand, if you take t greater than root k, then random sampling will do something non-trivial for you. So you won't get a k lower bound anymore. You'll get something like k squared over t squared. Okay. But in many cases, you'll see this coming up. We'll kind of get an upper bound on something, and that kind of amounts to maybe. The reason I chose this statement is this is the strongest thing. Even with a promise of such a large gap, you're not able to do better than omega k, which is pretty trivial.
Yeah, maybe the obvious statement is what you expect the magnitude of x, y to be is growth.
That's right. Okay, so before we plunge into more complicated things, I wanted to show you this 1 over epsilon 2/3 lower bound for equality. And I just like this proof because it's very visual. It doesn't use spectral yada yada and so on, right? So the point I'm trying to convince you of here is that this is not so much a reduction as it's kind of saying these two problems are the same thing, right? So suppose we have an instance of gap hamming that we wish to solve. I'm going to show you how to use a protocol for this collision probability, distributed estimation of equality, to solve gap hamming, right? So we have these two strings in plus minus 1 raised to k. I'm going to use these to come up with distributions on universes of size 2k, right? And the distributions are the most obvious ones you think about. I'll pair up these things so that I get k buckets. Each bucket has 2 elements. And depending on whether the bit is plus or minus 1, I'll put my mass either on the first bucket or the second bucket. So if xi and yi agree, they're both putting mass on the same element within, I use buckets wrongly. I put it on the first or second element. So if xi and yi agree, they put mass on the same element of that bucket. If they disagree, they put mass on different elements in that bucket, right? So each agreement is buying me 1 over k squared in terms of collision probability, and each disagreement means I don't add anything to the collision probability. So a root k gap in x dot y translates to a root k over k squared gap for this distributed estimation. Because remember, there are 2k buckets. The probability in each bucket is 1 over k. So root k over k squared is 1 over k to the 3/2. So what we're saying is 1 over k to the 3/2 gap for equality requires k bits of communication. You just rewrite this in terms of epsilon and you get exactly the statement that you want. Okay. Now we're going to see this equality lower bound again and again to the point where it will seem like I'm filling up time by showing you different proofs of equality. But this is really the point of this proof is that, I think to me it says these are basically the same question. Okay, but now to do reductions for other problems which are not so obviously the same as equality, we're going to just have this one important technical simplification. Suppose A in plus minus 1 raised to k times k. So this used to be 2 to the n before, now I'm calling it k because we'll reduce from gap hamming, okay? If it's the communication matrix for F, then a protocol for F with epsilon error lets you compute P transpose AQ for probability distributions P and Q. But I claim that you can jailbreak this protocol and run it on R and S for real valued vectors R and S. And the error that you'll get is epsilon times the 1 norm of R times the 1 norm of S. If R and S happen to be probability distributions, then you get back some order epsilon. But in general, this is just a convenience. You can also run it on real valued vectors R and S. So why is this true? Well, I'll take my R and I'll write it as the difference of two positive vectors, R plus and R minus. I'll do it the same for S. Now, at least I've gotten rid of all the negative elements, right? Now I'll run the protocol 4 times, taking all pairs into account. And if you stare at these are kind of measures. They're not probability distributions. But with a bit of renormalization, which I'm going to skip, you can do it. Okay. So now onwards, we are going to use this statement that epsilon error communication for F in distributed estimation gives us a protocol for computing this multilinear form, R transpose, bilinear form, R transpose AS. And we just need to keep control of what the one norm of the vectors R and S is. Okay. All right. So just to get our hands dirty with this, let's go back to equality and let's reprove this statement. So now we have XY. We don't need probability distributions anymore. So equality corresponds to the identity matrix. If you run it on XY, you will get exactly X dot Y, which is what gap Hamming is trying to compute. The error is bounded by epsilon times the one norm of X and Y. And these are Hamming vectors in the Hamming cube. Their one norm is K. So the error is epsilon K squared. When is this root K? Because that's the, so when epsilon is 1 over K to the 3/2, you get an error of root K. And that's where you need omega K communication. Right? It's the same statement. It's just slicker when you do it with real vectors instead. Okay. But let's do something different. We can also do greater than. I didn't show you the upper bound for greater than. It looks a lot like the protocol for absolute difference. But we can show that it requires a 1 over epsilon to the 2/3 lower bound. Here's the proof. Again, we're going to reduce from gap Hamming. This time, Alice will get X. Bob will get the greater than inverse times Y. We're doing this exactly so that when you compute R transpose greater than times S, the greater than inverse disappear, you get back X times Y. Okay. And now I need to know something about what happens to the one norms. So it's very useful to know what the inverse of greater than is. And you'll have to take my word that it is this matrix. He is laughing. He thinks it's obvious. I suspect this is actually the transpose of the inverse, but we won't, let's not get into that. So it's a very simple matrix. It only has 2 entries, non-zero entries per row. So the L1 norm of greater than inverse times Y, it's at most 2K, right? So whereas previously we got epsilon K squared, now we'll get 2 epsilon K squared. Asymptotically, nothing changes. You still require the same amount of communication. And this is kind of interesting because greater than itself does not have small spectral norm, but greater than inverse does. That's why its communication turns out to be 1 over epsilon to the 2/3, right? Because you take the greater than matrix, it's got a whole bunch of ones. So, you hit it with the right vector and you'll get something which has norm K or square root K. Okay. So this worked for these 2 matrices, but it felt like we were using some special properties of these matrices, right? Now let's try and come up with a generic reduction, which is going to work for any bounded matrix E. Okay. So as you can imagine, the SVD decomposition of the matrix is going to show up. We have this matrix A. We're going to write it as U sigma V transpose, where U and V are orthonormal matrices, and sigma is a diagonal matrix with the singular values sigma 1 through sigma k. And for the rest of this talk, the starring role is going to be played by this somewhat, well, I hadn't seen it before, this spectral quantity, which is the sum of the inverses of the singular values, right? So the sum of the singular values of a matrix is called its trace norm, I believe. So this is the trace norm of the inverse, if that makes you happier, but it is just what it is. It is the sum of the inverses of the singular values. So why is this important? Well, I'm going to do, in some sense, the obvious reduction, right? I start off with my instance of gap Hamming. Then I will take R to be X transpose U transpose divided by sigma raised to 1/2, which means I just take the square roots of all the singular values. And for S, I'll do Vy times sigma raised to 1/2. This is kind of the most symmetric form that we could think of, which gives us this very easy identity that R transpose AS is just X transpose Y. So what's going on is U transpose and U give you identity, V transpose and V give you identity, and then you have 2 sigma raised to halves, they cancel out the sigma. So it's something technical, but it works, right? And now, how much error does it give us? For this, we need to compute the one norm of these vectors, right? And, what are we going to do? We're going to use Cauchy-Schwarz. So we're going to bound the two norm instead. We'll incur a root k for that reason. This orthonormal part doesn't change anything. We can ignore it. We have a sigma raised to 1/2 in the denominator, right? So that's where this lambda a quantity comes from, right? So you get that this one norm is bounded by square root of k times lambda a. It's some calculation, and if you don't follow why this is coming, it's, you just write it down and that's what it is, right? It's not important to understand what's going to happen next. So now an epsilon error protocol for F gives us error epsilon times k times lambda a for gap hamming, right? Because each of these have one norm, which is square root k times lambda a. There's two of them, so it gets squared, right?
What was the relation between A and F?
Oh, A is just the communication matrix for F. So A for equality would be the identity matrix. A for greater than is the upper triangular all ones matrix. A for set disjointness is, it's, you think of these as strings, and Aij is Xi intersection Yj. It's just the zero in the Boolean case, it's just the 0, 1 matrix whose xyth entry is Fxy.
So what happened to discreteness in this statement?
Good, I'll come to that. So the general statement that we can abstract from it, which is unfortunately somewhat technical, is that small enough error, where small enough is 1 over square root k times lambda, right? That requires omega k communication. I basically said, what is the value of epsilon I can plug in here, which will give me square root k, because that is the hardest form of gap hamming. It turned out to be this somewhat ugly quantity, and that requires omega k communication. Good. So we're now going to see what this, so you can forget everything here except the definition of lambda a and the final statement, that as lambda a gets bigger and bigger, right? The lower bound that we are able to prove, it gets weaker and weaker in some sense, because now we are able to only say that extremely small error requires omega k bits of communication. Right? So the whole game is going to be to upper bound lambda a. So at this point, we've reduced the problem of proving lower bounds on the error dependence of distributed estimation to just proving upper bounds on this sum of the inverse of. So you wanted to know what happens for set disjointness, but of course I'm going to give you equality, right? Because I know the spectrum of the identity matrix. All the eigenvalues are 1. Lambda I, which is the inverse, is k. So if you plug it into this statement, it's telling you error 1 over k to the 3/2 requires omega k communication, which is the third time we're seeing the same statement again, but at least it's correct. It's giving you a tight bound for identity. Good. That's a start. Let's go back to greater than. Well, a fancier way of doing the same reduction we did before is to say that for the greater than matrix, all the singular values are greater than 1/2. This is again just because of the structure of the matrix. It's a very easy thing to verify. So how much this shouldn't be identity, this should be greater than, sorry about that. The sum of the inverses is bounded by 2k. So again, nothing really changes. Asymptotically, you require the same amount of communication. Okay, how about we do something interesting? Let's do a lower bound for inner product, right? Here the matrix is the Hadamard matrix. Again, we know the singular value of the Hadamard matrix. All of them are root k, right? And this is extremal for this reason. But now this lambda I quantity is really small because you're summing 1 over root k times. So you get root k, right? Now when you plug this in, you get a really strong lower bound, which says error 1 over k requires communication omega k. So remember I told you that for inner product, you need n over epsilon communication. Here I'm showing you a simple proof that 1 over epsilon is required. This doesn't talk about the n at all. Okay. Also, this is surprising to me because it felt like this, this gap hamming is tailor-made to prove lower bounds for equality, right? Because everything else is just diagonalizing the matrix. So therefore, the fact that you can prove a stronger lower bound than what you get for equality, it's surprising to me. But you just write it out and that's what you get. Okay, so error epsilon. So this tells us again the debiasing protocol is tight. Well, it also tells us that lambda A is going to be at least root k overall bounded matrices. Now, the boring way to do this would be to use AM, HM inequality, and so on. The more interesting way to do it would be to say that if you violated this, you would get such a strong lower bound, better than 1 over epsilon to the 1. You get 1.1, and that contradicts the debiasing protocol. So that's the right way to prove this statement. So yeah, the committee ignored our contributions to fundamental matrix inequalities. Okay, let's talk about absolute difference, which, as I said, is my favorite problem. The problem was this. We saw this weird protocol, which gave you 1 over epsilon to the 2/5. Where is the 2/5 coming from? Okay. Well, it turns out that when you construct the matrix, lambda for this absolute difference matrix is order k squared. This was proved in a paper in 1978 by Graham and Loash. So they were interested in shortest path metrics on trees and what these matrices look like, what their inverses look like. In the course of that, they had to invert the matrix absolute difference of I minus j, which is the shortest path on distance on the path, right? So that's why they were interested in this. Anyway, they proved this bound, and when you plug this in here, it tells you error 1 over k to the 2.5 requires communication omega k, and you stare at it, and it's exactly saying that our protocol is tight, right? So how did we find this result? You'd imagine that we just asked Avi, or Avi knew this already, and maybe he did, but that's not how we found it. We first we asked our favorite language.
I knew this because this year, not 20 years ago, there was a lecture in the special year last year on, by June Ho, that all this stuff with matrix. And someone talks about this paper.
Oh, yeah?
Yeah. It was, by the way, I'm not sure that Lobas is Graham and someone else who computed this shortest path of it. Maybe this result on the spectrum is Graham and Lobas, but Graham was at AT&T, they were looking at communication networks, and they wanted them to be trees, and they computed all sorts of things about it.
Okay.
So anyway, that's how I learned it only last year.
Okay,
But
good.
anyway, I didn't.
So 2 lessons. One, never assume that Avi has not seen a result in any part of discrete math or CS. The other, I'll actually tell you how we came across this result. I mean, you ask your favorite language model to look at this matrix and invert it. Okay. And then, you tell it to do the SVD, what are the asymptotics, you ask it that, and it seems to give k squared. So then you ask, okay, I just need this statement, forget about the matrix, prove to me that the sum of the inverses of this thing is order k squared, and it gives you a proof, which, who knows, and finally you tire of it and say, okay, find me a reference which proves this statement. And this took a long time, but it finally managed to prove it. And then you check that lemma 3 is indeed what it says it is, and then it gives you this problem state. I thought that was very impressive. Okay, so now we've seen that all these lower bounds are tight. Let's talk about this. Why Boolean functions are 1 over epsilon to the 2/3 hard, and then I'm done. Okay. So the claim is that in some sense, every full rank Boolean function, it's no easier than equality, right? And for Boolean functions, we've seen the Hadamard matrix where lambda A is root k, That's the smallest it can be. We've seen identity, where lambda is k, right? So if we were able to prove that lambda A is never much more than order k, we'd be done. We've seen the greater than matrix where it's 2k, right? But a theorem of the form lambda A is less than ck would imply for every full rank matrix. Of course, the matrix is not full rank, lambda is unbounded, right? So you have to throw in the full rank condition. But this also tells you why the statement might be false, right? What about matrices that are full rank, but barely? They are very poorly conditioned, right? There's this one singular value, which is non-zero, but technically, right, it's almost zero. And it turns out that Loga-Alan and Van Wu have constructed these anti-Hadamard matrices, where in fact lambda A is exponentially large on K. These are completely crazy matrices, right? Like if you look at the top few singular values, I think all the way up to the last one, you'll think it's the Hadamard matrix. But this matrix has determinant 1, which means the product of the singular values is 1. But there's just one small singular value which kills all the contribution from all these higher matrices.
This is a Boolean matrix?
It is a Boolean matrix. Yeah. And I think it's building on a construction of Hastad of this half space, which requires 2 to the n log n weights rather than just 2 to the n weights, which anybody could construct. So there's a lot going in there. Okay. So, I mean, this is a fantastic, this is an incredible object. But the question is, what does it mean for us? Like, this corresponds to some communication matrix, and we have to ask, are we scared of this matrix? And the answer is we are not. Because we will just reduce, if this were the matrix, we would just reduce from gap hamming in k-1 dimensions. We just pad the last entry with 0, right? And this, take my word for it, we're going to see it in the next slide. It will let us ignore this one small singular value. In fact, the lower bound we get for this matrix would be the same lower bound we get for Hadamard, which is 1 over epsilon, which is, we're just trying to prove 1 over epsilon to the 2/3 here, right? The moral of the story is that our spectral reduction is a bit more robust than we've been currently using. We don't need all the singular values to be well behaved. As long as there are many singular values which are not too small, we are in good shape, right? So here is a statement. If there are k minus t, if the bottom k minus t singular values, they don't look good to you, then reduce from gap hamming in just t dimensions, padded with zeros. So we'll start with xy in plus minus 1 raised to t, and we'll just take the summation xi ui by square root sigma I, right? What happened to the other singular values? Well, xi was 0 for all of them, so they just never showed up in my summation. Once I do this, then R transpose AS is still going to be the inner product in t-dimensional space. Okay? This, of course, came at a cost, because I took an instance in t-dimensional space and I embedded it into this larger k-dimensional space, right? Because the singular values, they are of a k-dimensional matrix, they still live in k-dimensional space. But you can chug through the reduction, and here is the statement. Let lambda t be the sum restricted to just the first t singular values, distributed estimation with error 1 over square root k times lambda t a, right? Requires omega t communication. So, it's kind of hairy. The point is the square root k is still there because that came from Cauchy-Schwarz, and we're still dealing with k-dimensional vectors. That did not change. This was lambda ta, that was the whole point of ignoring the small vectors. If you're starting from gap hamming in t dimensions and you get a lower bound which is k, then you've done something wrong. The lower bound had better be omega t. Okay? All right, great. Now, we want to say that equality is in some sense the worst matrix in this relaxed sense that all its singular values are 1. And in any full rank Boolean matrix, maybe you want to say that a lot of singular values are at least 1, right? And we can be very generous in this, a lot of singular values here because, sorry, oh wow. So I would be happy even with t, which is like, k over 100, right? Because that still gives me a linear lower bound. Even k over log k, k to the 1 minus epsilon would be fine, right? So we just need to find a short prefix for any full rank Boolean matrix where those singular values are not too small. Okay. So it suffices to show the sigma i's can't decay too fast. And here's what we'll say, that if you take t, which is k over 2 log k, right? Then the first t singular values will be at least 1/2. It's kind of like, it's like the greater than matrix, if not equality. But therefore, lambda TA is bounded by 2t. Right? And this will be good enough to prove what we want up to some logarithmic factor, which comes from the fact that it's k over log k. So why is this claim true? It's just a Markov inequality kind of in the exponent, right? It's a proof by contradiction. The only place where we are using Booleanness and not boundedness is to say that the determinant is at least 1, right? So that means the product of the singular values is at least 1, right? And now you can imagine that there's a tug of war between the large singular values and the small singular values to maintain this determinant to be at least 1. But unlike the small singular values, which can be incredibly small, the large singular values, they cannot be too large. This is just because of some Frobenius norm condition. The sum of the singular values squared is at most k squared, right? So nothing can be larger than k. So if you tell me that only t singular values are greater than 1/2, let's draw a line for large and small at 1/2. These will only contribute k raised to t. And if I chose my t correctly, this is something like 2 to the k over 2 that you're getting from the top. But now you're not going to be able to compensate for the bottom because these singular values are less than half. There's at least k over 2 of them. And they're going to contribute something which is much, much smaller than 2 to the minus k over 2. So you cannot have determinant 1. Right? So it's really using Booleanness in a very minimal way. If you start with the premise that your matrix has determinant 1, then in fact the conclusion still holds. But it's just interesting that a lot of these fairly natural matrices that we've seen, like absolute difference and so on, they happen to have very small determinants. So that's why you're able to get better upper bounds for them. Okay, so to finish this story, we had this robust version of our spectral lower bound. We combined that with this statement saying that for t, which is k over log k, the top t singular values have to be at least 1/2. And putting this together, it told us that every full rank Boolean function, in fact, requires r bar epsilon f to be at least 1 over epsilon to the 2/3. I'm only hiding some log or a couple of log factors in this statement. But one thing which came out of here, now let me go back to Yotham's question. What happens for set disjointness? Well, set disjointness, the spectrum is very easy to compute because the n by n set disjointness matrix, it's some kind of a direct product of a 2 by 2 set disjointness matrix. Half the singular values are greater than 1, half of them are less than 1. But for the greater than 1 part, this is the best we were able to show. And lambda k over 2a is order k. Okay? So I'm just taking the ones which are greater than 1. So each of them will give me at most 1. I think maybe you'll improve on this by some log factors, but not more than that. You're not going to close this gap. This is only going to give us a lower bound of 1 over epsilon to the 2/3, and the upper bound is 1 over epsilon. Even by the best, sharpest estimate for this, you're not going to close that gap. Okay. I've said all this before. Let me just, this is the school of math here. So here's a question that I would really like to know the answer to. It's not going to change any theorem that we have proved in a very significant way, but it's a clean enough question that I think we should know the answer to it. Consider all k by k full rank Boolean matrices. what is the smallest t, smallest going from 1 through k? How soon can you see a singular value less than 1/2? Okay. Now, what we've shown is that t needs to be at least k over 2 log k. You cannot drop before that. And again, apparently, and I haven't completely verified this, so you know what the source of this is, you can get upper bounds like 0.8k. Okay. But getting the singular values to drop sooner than that, it appears extremely non-trivial for Boolean matrices if it is at all possible. To the best of my knowledge, it's quite possible that the first k over 2 singular values have to be greater than 1/2. Right? So I don't know. We can only show k over 2 log k.
That's a very nice question.
Yeah. And it's interesting that you will need to use Booleanness, not just boundedness of the entries, because if the entries are bounded, you can just start with the sigmas as you like on the diagonal and do some, pick some random u and v, and probably things will be nicely.
Oh, put zeros everywhere.
But where will all put zeros? No, you want the singular values to behave pathologically, right?
I thought you can just put the singular values and put zeros elsewhere.
Singular values in the diagonal, but then you have to give me these two orthonormal matrices. Oh, sorry, you're saying just that. No, but you want this, sorry.
You want the singular values
want
to be
that full
k,
rank,
but
full rank.
to be
Full
bounded by
rank means
1.
no.
So you can do whatever you want in the diagonal. So you can do something like, I don't know if you can see this, but I can come up with a sequence like, let's say a bunch of root k's. So sorry, I'm trying to come up with a matrix where I see half very late into this thing, right? So just give me a second. Look, with the singular values, you can do what you want. Okay, so let me tell you how I'd construct a real matrix, which will show this k over log k boundless, right? Maybe you have a better way of doing it, right? I'll start with a stack with a sequence of root k's. And then I'll follow it up with a sequence of 1/2. This is the singular values. Well, that's great, but this finally needs to correspond to a bounded matrix, right? So where's the boundedness going to come from? I'm going to hit it with U transpose, with U sigma V transpose, where U and V are random matrices appropriately chosen. And maybe if I do it the scaling the right way, these will be able to kill these root k's in the entries, right? So you're going to get these entries like UI, the inner product of how these two matrices works.
Root k cancellation.
There's a root k cancellation. Thank you. Yeah, so there's a root k cancellation. So that's why it's going to work. That's why I just couldn't put k here, right? Root k was the right bound. That's why with reals, I think that this bound is essentially tight up to constants, right? But for Boolean matrices, I don't think, what do I know? But there's a big gap in our understanding of these things. Okay, great. So I think I'm pretty much done here. Let me just, there was a lot of results here. And, this is the first paper investigating this question. So I think it's right that, we explore the whole landscape, though I tried to highlight a couple of statements which I thought were particularly interesting. We have all these upper bounds. There's this RF over epsilon squared, R1 by F over epsilon. There's a couple of other upper bounds that I haven't shown you. If the matrix, communication matrix has bounded operator norm, you can always get that divided by epsilon raised to 2/3. So if your matrix has small operator norm, it's not particularly hard. You can get 1 over epsilon to the 2/3. There's also this other upper bound, which shows that when, why you need to talk about matrices of large rank. Otherwise, you can do things logarithmic and epsilon. In terms of lower bounds for Boolean functions, there was this classic bound of R of F. We've also showed a lower bound of 1 over epsilon to the 2/3 for full rank matrices, which I think is kind of interesting. If we didn't put all these problems together and stare at them like that, you wouldn't think that this pattern should even be true. So I think that's the nice thing about doing complexity, I guess. So in terms of N, we know that communication ranges between log n and n. Now, what we've learned is that for Boolean functions, in terms of epsilon for distributed estimation, the range is much narrower. It lies between 1 over epsilon to the 2/3 and 1 over epsilon squared, right? Now, when you talk about bounded functions, not just Boolean functions, then you get these interesting lower bounds which depend on the spectral properties. And what we do know is that as a function of epsilon, you can range anywhere from 1 over epsilon to some tiny power all the way to 1 over epsilon squared, right? Okay, so this is what we know. What do we not know? Well, a ton of stuff. What properties of a function make it hard for distributed communication? So hard means that the complexity is n over epsilon. You basically couldn't do anything better than the d biasing. Well, a trivial necessary condition for this is that, well, you need the function to be hard for randomized communication. Otherwise, you wouldn't get an n in the numerator here. Maybe that is sufficient. Maybe every function which is hard in Yao's model is also hard for distributed estimation. How do you think this is true? It is a curious coincidence that all the functions for which we were able to show a non-trivial upper bound, I guess I should say all two of them, they happen to also have non-trivial randomized protocols in the two-party standard model. It would be nice to know if this is a coincidence or whether, there's some reason the numerator and the dependence on n and dependence on epsilon are somehow tied together. Okay, this spectral bound has been, when you do it, it seems like some really hacky thing. You're getting some Cauchy-Schwarz, something else, and so on. Yet, except for set disjointness, it was tied for every function we've seen so far. Sorry.
It's okay, take a minute.
All right, let's try again. It would be nice if there were an upper bound in terms of lambda a, which explained this. But if you believe that the complexity of set disjointness is 1 over epsilon to the 2/3. So in terms of Boolean functions, we only know examples of functions where the dependence is 1 over epsilon to the 2/3 and 1 over epsilon. I'm sure there are others, but we don't know what they are. All right. I think I'll stop right there. Thank you.
Thanks for going all out of breath for us. Any questions or comments?
The talk started well and ended very tragically.
Well, the speaker is still standing. Okay, maybe we take you to lunch and then we can.
Yeah, thank you. Thanks.